Hocam yine durdurduğum yerden başlatıyordum. Kırmızıdan başlatıyordum.
Okay, let's talk about third generation, fourth generation, fifth generation. The fourth generation computers are personal computers, microcomputers, whatever you call them. These are the fourth generation computers. We have integrated circuits, but this time we have large scale integration. That means that we have more than a million transistors in a chip. So it made the computers much easier to run because smaller means that less power required. Also, smaller means that it is cheaper. Smaller means that you don't need to have very large boxes. So the computers became very cheap. 1980s. IBM, which used to produce lots of mainframes, very expensive mainframes, it started making computers, personal computers. So IBM needed some kind of an operating system to run on that computer, very light operating system. So it asked Bill Gates of Microsoft to develop an operating system for them. But Bill Gates didn't have an operating. He had an interpreter, he had a programming language, basic programming language interpreter for this kind of computers. He didn't have an operating system, but he bought another operating system, disk operating system from somebody else, and he sold it to IBM. So he made the fortune after it. You know, he's the. I mean, this much money, this much investment, $75,000 of investment for the disk operating system. It made him the richest person in the world right now, right? I mean, I guess he's the richest person of the history, I guess. He took the opportunity, he made it MS-DOS, and after 1980s, MS-DOS operating system, which was a very primitive, no good graphical user interfaces. Everything was in the form of small programs, but it was very small. You can fit the whole operating system in a 360 kilobytes of floppy disk. Okay, I remember using this operating system. I had my Pascal compiler, my operating system and everything on the same floppy disk. It was okay. I still have some space to spare. So it was a very small one. That's why it was very critical, very fast to boot up. But it wasn't that much advanced. It didn't have any protection. Resource management was bad. When you try to write to the operating system's memory, it allowed you. So when you do that, the operating system crashed a lot. So, I mean, when you are developing a program, maybe 2 out of 5 compilation your computer crashes, and you need to reboot your computer during those days. 1980s, the computers were so primitive with the personal computers, but with the mainframes and the mini computers, as I said previously, people were using on the graphical user interfaces with Windows icons and menus. And this idea was taken by some other people like Steve Jobs, and he made lots of money out of some other people's ideas. Microsoft and Apple didn't invent much. They didn't contribute much to the computer science or the computer engineering, the operating system. They just made it popular. When the things made popular, when they are popular, they became less expensive. When they are less expensive, more people bought them. More people buying lots of money brought many operating system researchers to the area. So that it was the way that they were useful. Otherwise, technically they didn't invent anything. Microsoft is making more inventions nowadays. Actually, it is than it used to do. But Apple is not doing anything useful for the computer industry. Okay, so this Microsoft NT was a milestone actually. Somebody from Vax VMS, operating system designer, came to Microsoft, and he designed this Microsoft Windows NT. Before this Windows version, all the Windows versions were very fragile. They used to crash a lot. They didn't have protection. It wasn't that advanced. So after Windows 18 2000, Windows started becoming a solid operating system. Nowadays what we are using, Windows 10, is a very, very advanced operating system with more than 80 million lines of code. Windows 8 had more than 80 million lines of code. Okay, Windows 10 should have even more than 8, so close to maybe 100 million lines of code for an operating system, which is amazing. Okay. So then after that we have the mobile computers, mobile revolution. Nokia, you remember Nokia? Maybe do you remember Nokia?
Yes.
Because sometimes when you say, I mean, anybody's remember this? This one?
No.
It was a very famous company actually. It was, so when I say everybody remembers that, I sometimes cannot judge it. So Nokia, they did lots of useful stuff actually. They invented they used to sell these devices, PDAs, personal digital assistants. Very, very small computers like this. It's a computer like that, but it wasn't a phone. So you put your calendar, you put your contact information, maybe a notebook, calculator, that kind of stuff. It's a personal digital assistant. So they came up with this idea of how come we are not putting the PDA and the phone in the same environment. It was called N9000, okay, in 1990s. And people kind of liked it, but they didn't buy it much because it was so expensive, maybe a little bit difficult to use. Then in 1998, Ericsson was the first. Ericsson was first to use this term smartphone. Okay, 1998, smartphone. So PDA and the phone at the same time. Then BlackBerry. It was very famous at the end of 90s and beginning of the 2000s. Then Apple came into the picture. They saw the opportunity. They said, okay, we're going to do the smartphone thing, but it's going to be very easy to use with a nice user interface and touch screen. Okay, so it was very successful. Then Google came into the play with the Android. So nowadays everybody is talking about iOS and Android operating systems. In how many years? In 10 years, right? And it is like infinity, I mean eternity, when you think about when the iPhone was released. I mean, you would say that maybe 30 years ago, something. No, it was 10 years ago, 9 years ago. These are not very, very old operating systems, but the idea is, the whole idea, they are both based on the Linux ideas or the Multics ideas. All of the ideas are coming from the Multics days, from 1960s. Okay? 1960s. So but there are extra requirements like the security and the battery management and that kind of stuff. If we have time, at the end of the semester, we might look at the more problems about mobile operating systems. This one is open source. This one is not. Apple doesn't make anything open source. It keeps everything as secret. So it is only after making money. It doesn't do anything useful stuff. This is the history of the operating systems actually. Most of the inventions happened in 1960s and 1970s. And nowadays you are using them over and over again. I will talk about this issue again because we'll say that whenever you see a new operating system problem, you should check the previously invented technologies and the problems. You should see some kind of a similar problem that people faced before, and after that you can continue from that time. Okay, let's come back and talk about the main operating system again. Why we are using operating system, what they are good for. Let's look at some computer hardware review, because we said that operating system is a piece of software that isolates from the hardware complexity from the user. That's why we need to look at the hardware in a little bit more detail. Okay, with the hardware, we have CPU. CPU you have to have CPU and the memory. Without these two, you don't have a computer. Okay, and these two are connected with a what? What is this?
Bus.
With a bus. Okay, just one or many buses. For the sake of simplicity, we are going to use a single bus here. Okay. How about this one? What is this? MMU.
Memory management unit.
Memory management unit. Memory management unit is a crucial part of the operating system abstraction. Memory management, CPU says that, okay, I want to write the number 5 to the 5th location in the memory, okay? Write number 5 to the 5th location in the memory, okay? Because the CPU thinks that there is a very large amount of memory available. This memory management unit takes that address 5, it converts that address to the physical memory address. Because CPU might think that it has a very, very large amount of memory, but in fact, it may not, okay? The memory might be very small, but CPU might think that, it can think that the available memory is very, very large, but in reality, that memory is not be that large. So, what does the memory management unit do? If the part of the memory that the CPU wants to access is inside the memory, okay, then it lets it write to that memory. Otherwise, it takes that information on the hard disk and puts it into the memory. So this memory management unit kind of fools the CPU. Okay, it makes it think that it has a very large amount of memory or smaller amount of memory, or it's addressing space. See, when my program runs, okay, let's say, in my memory, let's say if I have two programs, A, B, and C. This is address number 0, okay, this is, let's say, address number 1000, and this is, okay. When I load my programs A, B, C like that, okay, it's okay, they can run like that. But next time, when I switch, when I load them, C is loaded here and B is here. So the address all changes, right? So when C says that I will make an array, and the first byte of my array will be at address 1000, okay? When you load it again, it might be loaded here, so it becomes 2000. Who is going to handle it? This memory management unit handles it. So it changes the addresses on the fly, so that the process or the program running on the CPU thinks that it is always running at the same spot of the memory. Okay, so this is memory virtualization, and we are going to spend maybe 1/4 of this course, the whole semester, 2-3 weeks on this memory virtualization. Okay, on this memory virtualization. So the MMU is very important. We will talk about that later in a few chapters. Then we have these peripherals, monitors, keyboards, printers, the hard disk, and etc. There are many things. See, they are all connected to the bus, and they communicate with the CPU through this bus. Okay, keyboard and the USB. But between this peripheral and the computer interface, there is a video controller. This is a circuit, electronic circuit. Okay, electronic circuit. It talks to the peripheral, the computer hardware. Also, it talks to the CPU or the bus. Okay, it knows how to talk to both of them. These are specialized. Circuitry. They are provided by the producer of the hardware, the monitor producer, keyboard producer, printer producer, or the hard disk producer, and they are, as I said, they provide the signal interface between the computer and the CPU. They are difficult to understand. They are very difficult to use, and each one has its own controller device. So for a programmer to understand the details of video controller or the hard disk controller, remember, as I said, SATA interface. Okay, the interface, this device. If you wanted to understand this device, you need to read a few books, and the slightest book or the easiest book that you can read about this interface on this controller is like maybe 500 pages long. If you wanted to program the hard disk without using any other programs, programming directly this interface, you need to read those kind of books, and you need to write maybe 100,000 lines of code to write something to the hard disk. That's why it is not common to use these controls directly from the CPU. They come with their own software so that the complexities of these controls are abstracted away. These software, the software that comes with these controls are called device drivers. Device drivers. Without the device drivers,
Right.
without the device drivers, okay, without the device drivers, it would be very difficult to communicate with these hardware, okay. Device driver is a part of the operating system, but it is provided by the producer of the hardware. Okay. Producer of the hardware, and it runs in the kernel mode most of the time, and it makes our life easier to use all that hardware. Okay, let's talk about each of these one by one. First, the processor. Okay, without the processor, there is no computer. It's the brain of the computer. Okay, but its job is something boring. Okay, what it does is, okay, it fetches the instruction because it executes and then repeats it. Okay, the whole life of the CPU is this: fetches instruction because it executes and repeats. Okay, that's it. That's it. So the faster it does it, the better. It's more efficient. Okay, we already know that. And if the CPU is small and cheap and it doesn't produce much heat, it doesn't take much power, then that's the best CPU that we are going to have. Okay, CPU can have access to the memory through the memory management unit, but they have their own memory too. It's called registers. Okay, inside the CPU we have very small amount of memory. It's called registers. But they are much faster than the main memory. That's why you cannot have many of them. If you have many of them, CPU becomes very, very expensive. So you have to keep tens of them, maybe 50 or 60 of them. Okay. If you have a variable that you are constantly updating, then you use registers to keep that variable. And compilers are responsible for which registers are used for which variables. You usually don't deal with that kind of complexity. Some special registers. What is a program? Program counter is a register. It is used for what? PC. Program counter is used for, it's a register. It keeps the
Next program address.
it keeps the current or next instruction address. Which address, what instruction you are gonna fetch, okay? It shows you, it points to the address where you're gonna fetch your instruction. It's called program counter. After you fetch, decode, execute, you increment your program counter by 1. Unless the instruction you are executing is a branch instruction. Okay? If it's a branch instruction, then your program counter is modified like that. Another special register or registers, stack pointers. You know the stack from your data structures class. Stacks are used in very, very different places, many, many times with the operating systems. And to keep the top of the stack, you need pointers. Okay, this is my stack. Okay, to point to the top of the stack, I have a pointer, I have a register, and this register has to be, this address has to be, it is reached, it is accessed many, many times, so it has to be very fast. That's why you have special registers to show you the top of the stack, because you increment them, decrement them. Sometimes you do this. Okay, this is your stack pointer, right? Other than incrementing and decrementing, you do this: stack pointer plus 1, stack pointer plus 2. This means that I am accessing this local variable. Okay, if there is a local variable L1 and L2 and L3, this one accesses L1, this one SP plus 3 accesses here. Okay, so you do lots of arithmetic, pointer arithmetic with the stack pointers, stack registers. Okay, and then we have program status word, PSW. It has the condition bits. Condition bits, that means that what's a condition bit? Condition bit? the result of the last arithmetic operation. Maybe if you do some comparison, if the two numbers are the same, then this condition bit becomes 0. If the condition is bit 0, then branch. Otherwise, don't branch. Remember, don't branch. After the comparisons, these condition bits are updated. Okay, that's the program status word. And in this program status word, you have the kernel mode. Okay. If the kernel mode is 1, that means that your CPU is running in the kernel mode. It can do anything it wants. It can do anything it wants. Okay, in the kernel mode. Or sometimes with the CPU priority. If the CPU priority is very high for a program, then you put that information in this program status word. How do you set your kernel mode? Can I set my kernel mode myself? My program, I want to set my kernel mode to kernel mode. Not the user mode, but the kernel mode. How do I do that?
Change mode diye bir şey var büyük ama.
If you call that change mode instruction, and if everybody can do it, that means that everybody can run in the kernel mode, which is not good. You should not be able to change your mode to the kernel mode whenever you want. There should be some kind of a restriction. So how do I go into the kernel mode? If I am not allowed to use the change mode instruction, how do I go into the kernel mode? Only operating system should run in kernel mode. But how do I know that I am the operating system program? Yes.
We can use system call for kernel mode operation.
Yes, when you make a system call, say that, okay, I'm going to make a system call. When you make a system call, now the operating system is running. With the system call, it automatically switches to the kernel mode. Okay? So, you are not running in the kernel mode. It is the operating system running in the kernel mode. Without making a system call, you cannot go into the kernel mode. When you make a system call, it is not your code, it is the operating system code. Okay? So you cannot have your own system call. It has to be a system call. To obtain services from the operating system, if you are asking something, ask operating system to load some information from the hard disk. You need to make a system call. Ask the operating system to make a new process fork. Okay? You need to make a system call. When you make a system call, you are automatically in the kernel mode. But the code you are running is now operating system code, not your code. Okay? It traps into the kernel and invokes the operating system, which is a very crucial part of the whole operating system idea. You make a system call, you trap into the kernel mode, and you do everything you want. When the system call is done, you come back, and now you are in the user mode. Okay. So when you ask something to the operating system, your process is blocked. Operating system runs. When it comes back, your process can continue with the user mode. And the kernel mode, user mode flag is inside the PSW. Okay, with the CPUs, there is this important concept of pipelining. Remember what we said? CPU does this fetch, decode, and execute. They say that if the CPU does this all the time, why don't we have 3 parts inside the same CPU? One part fetches, the other part decodes, the other part executes. 3 parts. So when you are executing an instruction, the fetcher part is free and decoder part is free. So they say that when you fetch an instruction, okay, in the next cycle you are going to decode it, but then since this will be free, this can fetch another instruction. While this one is executing an instruction, this one can decode another one, this one can decode another one. So there are 3 instructions being executed at the same time. One is being fetched, one is being decoded, one is being executed. That means that your CPU is kind of running 3 times faster, because at the same time you have 3 instructions are being handled. Okay, this is called pipelining, and you already know this from your architecture class. Okay, from your architecture class, you already talked about this. Pipelining process. What is the biggest problem that the pipelining has to solve? There is a very serious problem with the pipelining.
Yeah.
What kind of hazards do we have? Data hazards.
Branch.
Call processors.
Yes, branching. When you are executing something here, it might affect the operator, one of the operands of the next instruction, right? When you write to some place, it might affect the operands of the next instruction. So when the instruction that you are decoding might be invalid. Or when this one is executing a branch, okay, then this one and this one is executing the wrong instruction. They are handling the wrong instruction. So those kind of hazards are there and they have to be solved by the CPU hardware. If there is a hazard, then that's why we don't like code that make lots of jumps, lots of calls, loop ends, because it makes these two phases invalid. Okay. Okay. More sophisticated version of the pipelining. You don't have a single pipeline, you have more than one pipeline. So in this case, 2 times speed up, 4 times speed up kind of, okay? But at the end of each pipeline, you don't have your execution yet, because sometimes the execution takes more than one clock cycle. You have many execution units. So you fetch, you decode, you put them in some kind of a memory. And from this memory, these execution units take those instructions and they execute it. This is called superscalar architecture. Okay, this is called superscalar architecture. Very, very advanced. Again, the number of hazards that can happen with this kind of structure is much more complicated than this one. So designing a CPU is not an easy task. It used to be much easier 30 years ago. Okay, there was no pipelining. There was no complicated instructions. There was no cache during those days. It was much easier with small number of transistors. But if you put millions of transistors on the same chip, you can do even more. When you do even more, then you will have these kind of problems. The hazards with this kind of superscalar structure is much more complicated than these ones. And you need to have special algorithms, specially developed algorithms to solve these problems. Okay, so with the CPUs, remember we are talking about the hardware. Without knowing the hardware, you will not understand the operating systems, because the task of the operating system is what? To isolate the hardware from the user. You should know your hardware at least conceptually, so that you understand the difficulties that the operating system designers are facing. Okay, with the CPUs we have this concept now, multi-threading and multi-cores. The man named Moore, you know who Moore is?
Yes.
Did he die? I think he died last year, 2 years ago. He is one of the founders of the Intel Corporation, the CPU maker. Okay, he said that beginning of the 1970s, he said that every 18 months, okay, we will have 2 times more transistors in a single chip. And the technology is like that. And the speeds are going to go up, and the prices will go down. At least they will. He said that for $1,000 next year, you are going to buy a computer with 2 times faster CPU or 2 times more transistor CPU. So when you make the CPUs faster, they heat up, they use more power, and that's a problem. Sometimes they don't want to do this. They don't want to make it faster. They want to put more transistors into the same CPU. So they say, okay, instead of having a single CPU on a single chip, now I have more than one CPU. Okay, I can run more than one thread or the part of the process. We will talk about that later. On a single chip. It's called multi-threading. So with the multi-threading, it's kind of, you have more than one CPU on the same chip, same device, and operating system has to handle it. Remember, we have multi-programming and time sharing. With the multi-threading available, I can actually run 2 programs at the same time. 2 programs at the same time. So which programs I am going to run? what is the scheduling, and what are the effects. If I run two programs at the same time, if somebody changes something in the memory, the other one might get affected at the same time. These are very serious problems to deal with, so multi-threading is something useful, but it comes with its own problems. Multi-cores, they are real multiple CPUs. I mean, with the multi-threading, some part of the hardware is shared, but with the multi-cores, you have real multiple CPUs on the same chip. Okay, so somebody took this idea even further. Instead of having how many cores do we have nowadays on the chips on the CPUs? 16 at most, 32. Do we have 32s? 16s are common. Okay, 16 core CPUs are common. With the GPUs, okay, graphical processing units, they have thousands of processing units on the same chip. Okay, they have many thousands of GPUs. GPU is not like a CPU. It can execute only a small subset of the instructions that a CPU can. Very, very simplified instructions, but it can execute them in parallel in a very, very fast way. Some people wrote very efficient programs that can run on GPUs, and sometimes if a 16-core CPU takes maybe 10 days to run a program, GPUs can do the same thing in a few hours. So it is 100 times, sometimes 1,000 times more faster. Sometimes you can get this kind of, if the problem is right with the GPUs, you can have these kind of speed ups. Very specialized hardware, but you need to write right program, correct program. Again, this is an example of a multi-threading, multi-core processor architectures. Types of CPUs. This is becoming very, very popular. And nowadays, these cell phones, they have the GPUs. All the computers, they have their own GPUs. They have CPUs, and on top of that, they have their GPUs. Some of the computers' GPUs are more expensive than the CPU itself. The nice thing is that you can put many GPUs on the same computer, which makes it many more cores, much faster programs run on a single computer. Okay, let's look at some architecture of the multi-threading, multi-core chips. Okay, if I have 1, 2, 3, 4 cores on a same chip, okay, this is the chip that I buy and put in my system, okay. There are 4 CPUs in it. With the CPUs we have the cache. What is a cache? Cache memory.
CPU'nun içinde kendi memorisi.
Well, yes, CPU has a memory. CPU has already memory, like the register, right?
Daha küçük.
What is the difference between cache and register? Yes.
Daha hızlı ulaşması. Oradaki data.
Registers are faster than the cache.
But cache is
But-
bigger than register.
Registers are slower than the cache, but the cache is faster than the main memory. Why it is faster? Because it is directly connected to the CPU. You don't have to use the main bus, to access these cache elements. Usually we have 2 or 3 levels of caches, okay? Level 1 cache, this one. Level 1 cache is much faster than the level 2 cache, but it is much smaller. Level 2 cache is slower than the level 1 cache, but is larger, but it is smaller than the main memory and faster than the main memory. You can have the third cache too. So in this architecture, each CPU core has its own L1 cache, but they are sharing this L2 cache. In this one, each one has L1 cache and L2 cache for its own. So what are the advantages and disadvantages of these two structures? I guess for this one, it will be much easier to handle the cache misses and hits, because each one has its own cache. The problem with this one will be what? What will be the problem with this one?
Synchronization.
Space mode.
Yes, synchronization between those cores, because I can have the same memory content in this L2 and in this L2 too. If core 2 is modifying some memory location, I might have the same memory location here too. So when two of them are working on the same memory location, it becomes a problem. You need to solve it. Either you have to undo it, or you have to invalidate the other cache's content. I can have the same problem with the L1 cache 2 here, but it is more common to have the same problem with the L2 cache. So it's just a single example of what kind of problems we might have with the multi-threading and multi-core chips. Okay, we are not going to talk much about this picture anymore, but it's more like a architecture kind of problem. Then most important hardware element in our computer other than the CPU, memory. We want our memory fast, very very fast. We wanted it as large. It should be as large as possible, and it is really cheap. And okay, I want it to be very 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 cheap. Not all of them can be satisfied at the same time. I mean, registers are so fast, but we cannot make them large. Okay, and they are not cheap. So with the register I can solve this problem. Main memory is kind of large, or maybe the disk, hard disk or tape drive. They are very very large, gigabytes of data, and they are very cheap, but they are not fast. So I cannot have all of them at the same time in a single hardware. So that means that I need to find some kind of in-between solution. The solution is this hierarchy. Okay. These are very very fast, but they are not large. They are expensive. Cache, a little bit larger, still fast, but expensive and small. A little bit larger, getting slower, and this is the slowest. See, they are getting slower and slower, but again, they are getting larger and larger. So this is our memory hierarchy. We have to learn how to live in this kind of a world. I cannot store all of my data in registers. I need to put some of them into cache. If it doesn't fit there, it has to be in main memory. If it doesn't fit there, it has to be here or there. And it is getting slower and slower. I don't want to. Okay, if I am okay with my program being slow, put everything in magnetic tape. It solves all the problems. But that means that my programs will be how many times? Million times, 100 million times slower. I don't want that, okay? I don't want slow computers, because when the computer is slow, I am wasting CPU time. The CPU can execute instructions very, very fast, but I am waiting for the magnetic tape to give me the next instruction. That doesn't work. So I cannot put all of my data here. I need to put frequently used data. Then if it doesn't fit there, then there. So who's going to manage this flow of data in this hierarchy? Operating system. And it's going to do it in a way that the complexity is abstracted from me. I will not realize where my data is. All my CPU is going to say that put number 5 in memory location 5. And I don't know where that memory location is in the main memory actually. Maybe it is in the main memory, maybe it is in the magnetic, maybe it works in maybe it lives in the cache. I don't know. But I know that my results will be the same. My results will not change. Okay. So this memory management thing is done by the operating system. Register and cache. Register a very very small amount. Okay. There are 32 registers for 32-bit systems and 64 registers for 64-bit systems. Node ile accessinde the CPU can access them in a single clock cycle. Okay. 2 of them, 3 of them at the same time. L1 cache is very small actually, 16 kilobytes sometimes. L2 is sometimes a few megabytes. So if you have a CPU, if your L2 cache size is large, L1 cache size is large, usually it is much better than having a high frequency CPU, high megahertz CPU, gigahertz CPU, because reading and writing data takes lots of time. If you have large cache hardware, then your programs end up running faster and faster. Okay? There are many problems with the cache. You looked at some of these with some of your classes actually. When do we put a new item into the cache? What kind of items we keep in the cache? Okay, which cache line to put the new item in? I mean, since cache is very small, I need to select a place to put my data in. The selection process takes some time and it takes some logic. Okay, when there is no space inside the cache, I need to remove some item from the cache. Okay, selection of that one. You don't want to remove an item that is going to be used in the next one cycle. That's the idea. And where to put the new evicted item in the larger memory. In the larger memory, because I have a hierarchy of caches and memory and the disk, where do I put, if I remove something, where do I put this removed thing? So all of these questions are difficult questions, but they have to be solved. And we are not going to solve them optimally. We will make some sacrifices and we will say that we are 80% efficient. We are maybe 75% efficient. You will never be 100% efficient with your memory handling. Your CPU, unfortunately, has to wait. Is going to wait for a while, and you will never be 100% efficient with your algorithms. Okay, disks are okay. So we are looking at this: registers, cache, memory, and the disks. We are looking at these disks. Okay, these are, we know they are larger, cheaper, but they are slow. Okay, because they are slow because they are mechanical. Nowadays, we are not using mechanical disks much. Okay, we are using solid state devices like the flash disks with flash drives. We are using those, but still they are, even though they are not mechanical, they are slow. Because of their architecture, their physical nature, okay? They are not mechanical, but they are slower. We keep them, okay, one of the properties of the disks are, their memory is permanent. Even if they don't have power, okay, available, they can keep the stored data, in those disks. And that's why we load our operating system and application from this, because they can stay there as long as we want without having any power. Even though we have more disk space in the disks on the disk drives, the allocation space has to be managed by the operating system. Okay, and you need to come up with a system of storing and retrieving files by name, by other properties, and of course, other people should not have access to my files on the desk. And these are all handled by the operating system. Let's look at this picture, and after the picture I will stop for today. Tomorrow, what is the time for the PS?
11.
10 to
From 10 to 12, right? Where? In this room? In this room? Z. Okay, I will do the lecture tomorrow. I will continue because I missed one lecture last week, and I'm going to miss another one in 2-3 weeks, okay? So I will do the lecture tomorrow, and I will do the lecture on Wednesday morning. So this week we will have 4 hours of operating system course, okay? No, 5 hours. 2 I already did. Tomorrow 2 hours, and Wednesday 1 hour. Okay, so this is the diagram of the physical hard drive. Okay, there are plates. These are plates, circle plates. I can write and read data on these plates. I can put data like 1 0 1 0 1 0 0 0 1 1 1 0 0. So this is called a track. I have tracks like that, and another 0 1 0 1 1. So it is using these tracks like this. I can store information, and this head it gets very, very close. It gets very, very close to the plate surface. It reads and writes. It reads and writes from this surface. And when you spin this disk, like 5,000 or 10,000 times per second, per minute, you are reading your data or writing your data in a very, very fast way. Okay. So I have many plates like that. Okay, on the order of 10. I have many plates like that. So I have many, many surfaces. In this one, it has 7 surfaces. And for the 7 surfaces, for each surface, I have a read-write head. Okay, I can move this read-write head in and out. So I can access any data on any. So this was designed in the 1960s again, and nowadays our disks are very, very small, and they store lots of data. In 1960s, the plate size was like this, okay, 60 centimeters. And it has a field, so all you can store was like 1 megabyte of data on a plate like that. Nowadays I can store terabytes of data on a smaller, very small disk space. But the idea is the same, only the scale has changed. The technology stays the same. Something is spinning and the read-write head is moving in and out and then transferring data to the computer. The idea is the same, technology is different. Okay, that's it for today. Tomorrow at 10 a.m. we will continue.